Welcome back to Basic Electronics. In the previous class, we have seen the broad meaning of edge-triggered flip-flops. We will now look at one of the most important elements in this category, the JK flip-flop. In particular, we will consider the master-slave configuration of the JK flip-flop and describe its transition table with the help of an example. After understanding the basic operation of the JK flip-flop, we will work out the output waveforms for a JK flip-flop with some given input waveforms. Okay, let us get started. Let us now discuss the JK flip-flop, in particular the master-slave configuration. So here is the complete circuit for the JK flip-flop. These are the inputs, clock, J and K, and the outputs are Q and Q bar. Now within the JK flip-flop, we have a master part, this one, and we have a slave part. Alright, now the slave part looks very familiar. It is nothing but the clocked RS latch that we saw previously, and the master part is also familiar, except we have these three input NAND gates now. This input is coming from Q bar of the JK flip-flop, and this input is coming from Q of the JK flip-flop, like that. Both of these get the clock signal. This one gets it directly, and the second flip-flop, the slave flip-flop, gets it after inversion. When clock is 1, then there is a possibility of Q1 changing, depending of course on these inputs, J and K and Q bar. And at that time, clock bar is 0, so therefore R2 and S2 are both equal to 1, and as we have seen before, the output of the second flip-flop, the slave flip-flop, cannot change. In that case, it continues to be whatever it was. Now consider the other situation. When clock is 0, then this R1 and S1 are 1, and in that situation Q1 cannot change. Clock bar is then 1, and therefore we can see Q and Q bar change, depending of course on these inputs here. So in summary, if clock is 1, then the master is active, the slave is not active because its outputs cannot change in that interval. When clock is 0, then the master is inactive and the slave is active. So here is the summary. When clock goes high, only the first latch is affected, the master latch. The second latch retains its previous value. And when the clock goes low, the output of the first latch is retained. It continues to be whatever it was. And Q1 can now affect Q. So now there is a possibility that the slave output can change. In other words, the effect of any changes in J and K appears at the output Q only when the clock makes a transition from 1 to 0. When clock is 1, the data affects Q1, J and K values, and when the clock goes 0, then this change gets transmitted to the output. So that is how it works. This is therefore a negative edge triggered flip-flop, because we require the clock to be high and then go low. And now it should be clear why this configuration is called the master-slave flip-flop. When J or K changes, that change affects the master first and can cause Q1 to change, and the slave then simply follows. So this change in Q1 then affects the output of the slave flip-flop, which is Q. Alright. Now here is the transition table for the JK flip-flop. the JK master slave flip-flop, and we come across this new symbol now that indicates a negative going edge in the clock. That means the clock is going from 1 to 0. So only if that happens, all of these entries are valid. There is this new notation now, Qn plus 1, and that is used to denote the value of Q after the nth clock pulse. And by the same token, Qn means the value of Q before the nth clock pulse. And as we look at some examples, the nomenclature here will become clear. Alright, now let us look at this truth table. If J and K are both 0, then Qn plus 1 is the same as Qn. If J and K are both 1, then Qn plus 1 is Qn bar, that means the inverse of what it was earlier. If J is 0, K is 1, then Qn plus 1 becomes 0, independent of its past value. And similarly, if J is 1, K is 0, then Qn plus 1 becomes 1, irrespective of its past value. And this is a new feature. Note that the JK flip-flop allows all 4 input combinations. That is something that did not happen with the RS flip-flop. Let us look at some waveforms now for the master-slave JK flip-flop, which we saw in the last slide. Here is our clock, and the active edge of the clock is indicated with this arrow here. And in this case, that's a negative going edge, because our flip-flop is a negative edge triggered flip-flop. This is the J input, and that is the K input. And as a result of these input conditions, we want to figure out how these variables R1, S1, Q1, R2, S2, Q are going to vary. Q, of course, is the output of the flip-flop. In the beginning, we will assume that Q is 0. Let us start with some observations before we begin with the plot. These variables R1 and S1 would be 1 if the clock is 0, and that holds irrespective of the other inputs. And similarly, R2, S2 would be 1 if clock bar is 0. That means clock is equal to 1. So in these intervals, when a clock is 0, here or here or here, we are going to have R1 and S1 equal to 1 as shown here. And in these intervals, this one, this one, this one, and so on, we are going to have R2 and S2 equal to 1. So that is something that we can draw without even thinking of the other inputs to these gates. Let us consider this interval in which clock is high, and as we just mentioned, when clock is high, R2 and S2 are 1, no matter what the other variables are. And what can we say about Q? If R2 and S2 are 1, R2 equal to 1, S2 equal to 1, this latch will hold its output, and therefore Q does not change. So Q remains equal to 0. Alright, now let us look at R1. When clock is 1, that means this input is 1. R1 is the NAND of J and this input, which is Q bar. And since Q is 0, Q bar is 1, J is also 1, and therefore R1 is equal to 0. What about S1? S1 similarly is the NAND of K and Q, and since K is 0, S1 is going to be 1. Now if R1 is 0 and S1 is 1, that means Q1 is going to be 1. That is what we have shown over here. Let us now talk about this interval in which clock has become low once again. And as we discussed, R1 and S1 are going to be 1 in this interval. If R1 is 1, S1 is 1, then this latch is going to hold its output, which is Q1. So therefore Q1 cannot change. So we have R1 equal to 1, S1 equal to 1, and Q1 remains what it was. What about R2? R2 is simply Q1 bar, because this input is now 1, and that is what happens here. Q1 is 1, so R2 is 0, and S2 is the complement of R2, that is equal to 1. And now because R2 is 0 and S2 is 1, the output of this latch has changed to 1, and that is what we have shown over here. So the flip-flop output has now switched from 0 to 1. Next, let us take this interval in which clock is high, and as we discussed earlier, in this interval R2 and S2 are going to be 1, and because R2 S2 are both 1, Q cannot change, and that is what we see over here. Alright, what about R1? R1 is the NAND of J and Q bar. Our J is 0, so R1 is going to be 1. What about S1? S1 is the NAND of K and Q. Q is 1 and K is also 1, so therefore S1 is going to be 0. If R1 is 1 and S1 is 0, that means this latch is going to be reset to 0, and that is what we see over here. This interval now, clock is 0, so R1 and S1 are going to be 1, and Q1 is not going to change, like that. R2 is Q1 bar, so that is 1. S2 is the same as Q1, that is 0. And now with R2 equal to 1 and S2 equal to 0, Q is going to be reset to 0, the output of this second latch. Next, this interval in which clock is high, and we know that R2 and S2 are going to be 1 now, and therefore Q is not going to change, like that. What about R1? R1 is the NAND of J and Q bar. Q bar is 1 and J is also 1, so therefore R1 has gone to 0. What about S1? S1 is the NAND of K and Q. K is 1 and Q is 0, so therefore S1 is 1. If S1 is 1, R1 is 0, Q1 is going to change to 1. Next interval, clock is 0, so therefore R1 is going to be 1, S1 is going to be 1, and Q1 is not going to change. What about R2? Is the same as Q1 bar, and S2 is the same as Q1. So we have S2 equal to 1, R2 equal to 0, and therefore Q is going to change from 0 to 1. In this interval, clock has become 1, therefore R2 and S2 are going to be 1, and Q will continue with what it was, like that. R1, NAND of J and Q bar. J is 0, so therefore R1 will be 1. S1, NAND of K and Q, and K is 0, so therefore S1 is also going to be 1. So we have R1 equal to 1, S1 equal to 1, so Q1 is not going to change. So that is what the situation is in this interval. Alright, the last interval now. We have clock equal to 0, so therefore R1 is going to be 1, S1 is going to be 1, Q1 will stay where it was, like that. R2 is Q1 bar 0, S2 is the same as Q1, so 1, and Q will be determined by S2 and R2. So if S2 is 1, R2 is 0, Q will be equal to 1. So that is our overall flip-flop output waveform as a result of these input conditions. So as we have seen, a lot of activity goes on inside this circuit when we apply some input conditions like these, and it can get a little mind-boggling sometimes. But there is some good news, and that is we have this transition table, and we can use this table to go from the input conditions directly to the output Q of the JK flip-flop. and let us see now how that can be done. Let us start with q equal to 0, and from this table we know that q can change only after a negative clock edge. So only after this time can q change, and now let us figure out whether q changes from 0 to 1 or it remains equal to 0, and that is decided by this table entry here. So just before this active edge, which is the negative edge in this case of the clock, let us look at the values of j and k. So just before that edge, j is 1 and k is 0. Now let us refer to this table, j equal to 1 and k equal to 0, and qn plus 1 is 1 here. So therefore the output is going to change to 1 at this point, and then nothing is going to happen to the output until the next active edge comes, that one. And what is the situation just before this active edge? J is 0 and k is 1, and that brings us to this row. That means qn plus 1 would be 0, and that is what happens over here. Again nothing changes up to the next clock edge, the next active edge, and before that transition, just before that, we have j equal to 1 and k equal to 1, which means our qn plus 1 is going to be qn bar. So that means the output is going to toggle. Since it was 0 earlier, it's now going to become 1. And once again, the output will stay constant up to the next clock edge, which is that one. And before that clock edge, we have j equal to 0, k equal to 0. That brings us to this entry in the transition table, and that says that qn plus 1 is equal to qn. That means q will continue to be what it was. Since it was 1, it will continue to be 1. So that is how simple it is. We really don't need to tax our minds with what goes on inside the flip-flop, and this transition table makes things nice and easy. JK flip-flops can be made either as positive edge triggered flip-flops or negative edge triggered flip-flops. We have already looked at the functionality of this one earlier. That is the transition table for a negative edge triggered flip-flop. And similarly, here we have a positive edge triggered flip-flop, and that is the table for it. The only difference is here we have a positive going clock edge as the active edge. Here we have a negative going clock edge as the active edge. Otherwise, these entries are identical. And commercially, both negative and positive edge triggered JK flip-flops are available as ICs. Here are some examples. We would now like to make a very important point about the operation of JK flip-flops, in particular edge triggered JK flip-flops, and we will do that by taking a negative edge triggered JK flip-flop as an example, as shown here. This is the clock. These are the active edges. The positive edge is denoted by T1A, the negative edge by T1B for the first clock pulse, and for the second clock pulse, the positive edge is T2A and the negative edge is T2B. As we have seen earlier, when clock is high, for example in this interval between T1A and T1B, the J and K inputs determine the state of the master latch. The output of the master latch is Q1. During this time, clock bar is 0, and therefore the slave is not enabled. Its output does not change. That is, Q does not change, and Q is the flip-flop output. So during this time, we don't see any change in the flip-flop output, although things are happening inside the flip-flop in the master part. Alright. Now when the clock goes low, the slave flip-flop becomes active. The master does not allow any changes anymore in Q1. The slave flip-flop becomes active, and now this change which happened in Q1 in the earlier phase, that is clock equal to 1 phase, it gets transferred to the slave output, which is Q. In short, although the flip-flop output Q can only change after the active edge, that means just after T1B or T2B, the new Q value is determined by the J and K inputs just before the active edge. That means just before T1B or just before T2B, etc. So in order to figure out what's going to happen to the flip-flop output after the active edge, we need to look at the inputs just before that particular active edge. And that is a very important point, and we must remember this point when we look at circuits which involve JK flip-flops. Let us now look at an example, and let's start with the positive edge triggered flip-flop. Here is the transition table. These are our inputs, clock, J and K, and Q is given to be 0 in the beginning. Alright. Now the first change that we expect can only happen after the active edge, which is a positive edge in this case. And in order to figure out what that change is, we need to look at the J and K inputs just before this edge. And in this case, J is 1, K is 0. We now go to this table, J is 1, K is 0. So Qn plus 1 is going to be 1. And that will happen just after the active edge. So that is what we see over here. Next change will happen at this active edge. And just before that, J is 0, K is 0, and in that case Qn plus 1 remains equal to Qn, so therefore this Q equal to 1 will continue until we come to the next clock edge, the active edge. At that point, or just before that active edge, we have J equal to 0, K equal to 1, and then we expect Qn plus 1 to become 0, and that is what we see here. The next active edge is here. And just before that, we have J equal to 1, K is also equal to 1. So we look at this entry in the transition table, and we see that Qn plus 1 is Qn bar. That means the output of the flip-flop toggles. And since it was 0 earlier, it will become 1, like that. And after that, we have this active edge. Before that, we have J equal to 0, K equal to 1 there, and therefore Qn plus 1 will become 0, like that. And when the next active edge comes, this one, just prior to that we have J equal to 0, K equal to 1, and Qn plus 1 then becomes 0, and since it's already 0, we don't see any change. Let us now consider the same inputs being applied to a negative edge triggered JK flip-flop. And as we have commented earlier, the only difference between the two transition tables is the active edge. We have a positive clock edge as the active edge here. Here we have a negative clock edge as the active edge. And you are encouraged to go through all the transitions in the waveforms and verify that the Q waveform looks like this. To conclude, we have looked at the JK flip-flop, in particular the master-slave configuration. We have seen why the J and K input values just before the active edge determine the output of the flip-flop just after the active edge. This is an extremely important point and is therefore worth repeating here. Although the master-slave JK flip-flop is a complex circuit, we found that its behavior can be represented by a simple transition table, and using this transition table we worked out the output waveforms for a JK flip-flop with some given input waveforms. In subsequent lectures we will look at some practical applications of the JK flip-flop. Until then, goodbye.